So the handle of this titanium mug is joined to the body by welding. So this mug is made out of metal, and the handle is just welded to the mug. At the welding temperature, the titanium reacts with the oxygen in the air, forming an oxide. The oxide makes the weld more brittle. The chemical properties, such as reactivity, depend on the element's electron configuration. So there's a bond, even though it's titanium, that's connecting that handle to the mug. So what we're going to talk about is, we're going to address this question. When is an atom unlikely to react? And the answer is, or the next thing is, when the highest occupied energy level of the atom is filled with electrons, the atom is stable and not likely to react. So we've been talking about valence electrons and the magic number of 8. So the chemical properties of an element depend on the number of valence electrons. An electron dot diagram is a model of an atom in which each dot represents a valence electron. So the symbol in the center represents the nucleus and all of the electrons in the atom. So here's the grouping. So in group 1, they have one valence electron. So we would say H and then a dot. Now, group 2 has 2 valence electrons. Now, if you don't remember what a valence electron is how many electrons there are in the highest energy level for that particular element. Group 3 has 3 valence electrons. Group 4 has 4 valence electrons. Group 5 has 5 valence electrons. Group 6 has 6 valence electrons. Group 7 has 7 valence electrons. And how many valence electrons do you think there are in group 8? 8, okay? Except for helium. Helium's the only one that doesn't have 8. But remember, on that first energy level, that first ring, 2 electrons is all the room that they have, okay? But the rest of them are 8. So then noble gases are the most stable. Those are the ones all the way to the right in group 8. They have the highest occupied energy level of a noble gas atom is completely filled. In other words, it has 8 valence electrons. That's the magic number. The noble gases have stable electron configurations with 8 valence electrons, 2 electrons in the case of helium. That's because that first ring can only hold 2 electrons, but it's stable is the point. Elements tend to react to achieve electron configurations similar to those of noble gases. Okay. So then, what is the way in which elements can achieve stable electron configurations? Some elements achieve stable electron configurations through the transfers of electrons between atoms. So chlorine atom has 1 electron fewer than the argon atom. Adding 1 electron would give chlorine a stable configuration. A sodium atom has 1 more electron than a neon electron, or a neon atom. Removing 1 electron from the sodium removing 1 electron would give sodium a stable configuration. So this is a table salt. This is what we're talking about. So sodium reacts with chlorine. The electron transferred in each sodium atom to a chlorine atom. Each atom ends up with a more stable electron arrangement than it had before. So sodium is Na. It has 1 valence electron. Chlorine, Cl, has 7 valence electrons, and they form a bond, and they kind of end up with 8 valence electrons, if you want to think about it like that. So what happens is that the sodium will give 1 electron to chlorine, and when it gives off that 1 electron, it loses its charge, a negative charge. So the sodium has a positive +1 charge, and because chlorine takes on the extra electron, it has a -1 charge. And then the charges are attracted to each other because positive is attracted to the negative, and they kind of cancel each other out. And by the way, that's salt, table salt. So that's how these, we're going to be talking about ionic bonds. So the formation of ions basically, when an atom gains or loses an electron, the number of protons is no longer equal to the number of electrons. The charge of the atom is not balanced, and the atom is not neutral. An atom that has a positive net or net positive or negative electric charge is called an ion. The charge on an ion is represented by a plus or minus sign. So if you want, when we talk about an ion that forms when a chlorine atom gains an electron, has 17 protons and 18 electrons. So this ion has a charge of -1. That extra electron, in other words, normally chlorine has 17 and 17. But when it takes on that extra electron, it has a -1 charge. So you could write the number there, and usually if it's just a 1, you don't need to put the 1. But if it's, you can have a +2 or a -2, and then you got to write in the number. But anyways, an ion with a negative charge is called an anion. Okay? Anions like the chlorine ion are named by using a part of the element plus a suffix like "ide." So the Cl with a negative charge of 1 is called chloride instead of chlorine. So when we say salt is sodium and chlorine, it's really the name is sodium chloride, right? So sodium has a charge of +1 because when it gives up an electron, the balance shifts. It has 11 positive protons and 10 negative electrons. So the charge then is +1. You just write the symbol down, and you could say 1 plus or just the plus sign if it's a charge of 1. And then that is called a cation. So there's two terms we're going to talk about a lot in this section: anion and cation. Now, how I remember which is cation has the letter T in it. The letter T looks like a plus symbol. So I remember that cation is the positive ion. That's how I remember it. And the cation uses an element name such as sodium ion, right? So that's why it's pronounced sodium chloride. Formation of ions. Scientists use atomic radii to compare the sizes of atoms of different elements. The radius of a sphere is the distance from the center of the sphere to the outer edge, half the diameter, basically, of a ball. Think of a ball. So the atomic radii is plural for radiuses, are extremely small. They are expressed in units of picometers. They are 1 billion, or 10 to the -9 picometers in a milliliter, or millimeter, okay? Another term you'll hear is that a common measure of unit is 10 to the -10, which is an angstrom. So in this table, we show that the atomic radius and ionic radius for 6 metals and 6 nonmetals. You could use this data to relate the size of the element's atoms to the element's location on the periodic table, okay? And then compare the sizes of the atoms and their ions, okay? So when you look at that, well, just kind of soak that in for a minute. There's a pattern. So basically, when you look at this right here is the ionic radius, okay? And this is the atomic radius. Just kind of process that. So using the table, within a period, what happens to the atomic radius and the atomic number of elements as the atomic number of elements increases? Well, within the period, remember the period is going to go across this way. It's a row. The atomic radius decreases and the atomic number increases. So just kind of, it seems counterintuitive, right? Because you're going to have more stuff over here on the right, but the radius decreases. That's to make room for all the electrons and stuff. Within the groups 1A, 2A, 6A, 7A, what happens to the atomic radius of the elements as the atomic number increases? Well, in that case, within the groups themselves, the atomic radius increases as the atomic number increases. In other words, what they're saying, we start off with 152, so I've got an atomic radius, so lithium has an atomic radius of 60. Then when I go to sodium, I have an atomic radius of 186, and then an ionic radius of 95. So these numbers increase, okay? How does adding the occupied energy level affect the atomic radius? In other words, lithium is a period 2 element and sodium is a period 3 element. So they're saying what happens from here to here. When the next higher energy level is occupied, there is a significant increase in the atomic radius. So we go from 60 to 95. Okay. Compare the atomic and ionic radius for potassium and for bromine. So you almost see a flip-flop. Like if you look at this, the atomic radius is 227. Over here, though, the atomic radius is 114. The ionic radius for potassium is 133. And then the ionic radius for bromine is 195. So the ionic radius for potassium is much smaller than its atomic radius, and the ionic radius of bromine is much larger than its atomic radius. So then how do we generalize this? What happens to the radius of an atom when the atom loses electrons or when the atom gains electrons? So in this particular case, it will lose an electron. So that's the difference between these numbers. The ion will lose an electron. And over here, the atom will gain an electron if we think about ionic bonds. So with the loss of valence electrons, and I should carefully say that when we lose electrons, these are valence electrons always, the radius decreases. With the addition of a valence electron, the radius increases. So explain the difference in size between a metal ion and its cation. So the energy level that is occupied is no longer occupied, so the size decreases, which kind of makes sense when you think about it. So the formation of ionic bonds occurs when a particle with a negative charge will interact with a particle with a positive charge. Remember that opposite charges attract. So a chemical bond is the force that holds atoms and ions together as a unit. An ionic bond is the force that holds cations and anions together. An ionic bond forms when electrons are transferred from one atom to the other. So we're going to learn about lots of ways that these atoms are connected to other atoms to form molecules to make up everything. The first one that we're going to talk about today is the ionic bond. And basically an atom will give off an electron or 2 or 3 to an atom that needs 2 or 3 electrons to be stable in that outer energy level. The magic number is 8. And so we call that an ionic bond. It literally gets rid of an electron, and the other one literally gains an electron. One is positively charged, one is negatively charged. They're attracted to each other. Boom, they're stuck with each other. Okay? So cations form when electrons gain enough energy to escape the atom. The energy allows the electrons to overcome the attraction of the protons in the nucleus. The atom of the energy, or the amount of energy used to remove an electron, is called the ionization energy. The lower the ionization energy, the easier it is to remove an electron from an atom. Similar thing takes place when you think of solar panels. There's electrons, valence electrons kind of going around, and we kind of rig the solar panels in a way that makes it easy for the electrons to leave. But essentially, the light energy, the electromagnetic radiation, is absorbed by the electron. It has extra energy and it escapes the atom. So then this figure shows 2 trends in ionization energy. Basically, generally, this will decrease as we go down, and the ionization energy will increase as you go to the right. So how does the structure of an ionic compound affect its properties? Well, the solids whose particles are arranged in a lattice structure are called crystals. So these electrons are in certain parts, and the molecules will form bonds based on the location of the valence electrons and the charges in a very structured way. Well, not always structured, but we call those crystals. The properties of an ionic compound can be explained by the strong attractions, though, among the ions within the crystal lattice. So the compounds that contain ionic bonds are ionic compounds, which can be represented by chemical formulas. So a chemical formula is a notation that shows what elements of a compound contains and the ratio of the atoms and the ions and those elements in the compound. So the chemical formula for sodium chloride, which is just plain old table salt, is Na, which is sodium, Cl, which is chlorine, and it indicates that there's one sodium ion for each chloride ion. What about magnesium chloride? Well, magnesium, so let's back up. Magnesium has 2 valence electrons. Chlorine has 7 valence electrons. So this chlorine atom needs 1. This chlorine atom needs 1. So if the magnesium gives up 1 electron to this chlorine atom and gives up 1 electron to this chlorine atom, then I need I have a positive 2 charge on magnesium and a negative 1 here and a negative 1 here. So when there is a chemical or a molecular structure in an ionic bond, the charges will always equal 0, because atoms are going to be giving off electrons. That gives them a positive charge. Other atoms are going to be gaining electrons, and they're going to have a negative charge, and the charges should always equal 0. So a magnesium atom cannot reach a stable electron configuration reacting with just one chlorine atom. It must transfer electrons to 2 chlorine atoms. After the transfer, the charge of the magnesium ion is +2, and so the symbol is Mg2+. The formula for magnesium chloride, though, is MgCl sub 2. And the 2 written to the right and slightly below, and we call that subset notation, is a symbol for chlorine. And basically what we're saying is for every magnesium atom, I have 2 chlorine atoms. Magnesium chloride is used to control dust on unpaved roads. So crystal lattices, basically a chemical formula for an ionic compound tells you the ratio of the ions of the compound, but not how the ions are arranged. If you look at a sample of sodium chloride with like a handheld lens, like one of those Sherlock Holmes type things, or even under a microscope, you'll see that pieces of salt are shaped like cubes. There's a structure there. The crystal shape is a clue how the sodium and the chloride are arranged in the compound. Ions in sodium chloride are arranged in an orderly 3-dimensional structure pattern. So for each chlorine ion surrounded by 6 sodium ions, each sodium ion is surrounded by 6 chloride ions. Each ion is attracted to all the neighboring ions with the opposite charge. This set of attractions keeps the ions fixed in a rigid framework, which we call a lattice. So this is an example of it. This is what it looks like at a molecular atomic level. This is the structure, always. And then this is what we actually see. Okay, so a sodium chloride crystal, so this is like a very tiny piece of salt, or it could be a big piece, I don't know. But a little grain of salt looks like this, if you were able to look at the atoms. So each ion is surrounded by 6 oppositely charged ions. Sodium chloride crystals are shaped like cubes. Okay, so this is a crystal and how it's shaped based on this construction. All right. So the shape of the ionic crystal, for example, the cubic shape of the sodium chloride crystal depends on the arrangement of ions. The arrangement of ions depends on the ratio of ions and their relative sizes. Crystals are classified in groups based on the shape of their crystals. So the property of sodium chloride are typical of ionic compounds. Sodium chloride has a melting point of 801 degrees Celsius. Remember we talked about that? You can melt salt, but it's got to be really, really hot. Solid sodium chloride is a poor conductor of electricity, but when it's melted, it's a good conductor of electricity. Sodium chloride crystals shatter when struck with a hammer. And basically you're breaking those the ionic bonds. So the arrangement of particles in a substance is the result of two opposing factors, the attractions among the particles in the substance and the kinetic energy of the particles. So this is very similar to phase, but you're dealing with more than one atom. The stronger the attractions of the particles, the more kinetic energy the particles must have before they can separate. Right? So you just picture something kind of being held together by a force or attraction. And the more they're held together, the harder it is to pull them apart. But it's the movement, the kinetic energy. I got to keep moving and to break them apart. So ionic compounds have strong attractions between the particles and high melting points. Although there is a lot of research on what we call ionic liquids, and those are salts that are liquids at room temperature. But most salts are solids. Actually, there's quite a bit of quite a large hundreds and hundreds of ionic liquids. But anyways, for the electric current to flow, the charged particle must be able to move from one location to another. So ions in a solid crystal lattice have fixed positions. Sodium chloride is a poor conductor of electricity because the electrons are fixed. One is given away to the other one, and because of the structure, it just doesn't move around. That's why elements tend to be better conductors of electricity than compounds. So when a solid melts, the lattice breaks apart, the ions are free to flow. Molten sodium chloride is an excellent conductor of electricity or electric current. An ionic crystal, if it's struck, the ions are in a fixed position, but you can break the bond. So this positive ion is attracted to this negative ion is attracted to this one and this one. If I give it enough energy, and this would be kinetic energy, the hammer will hit these ions and it'll break apart. So just to kind of review real quick, when is an atom stable? When the highest occupied energy level is filled with electrons. Usually 8 valence electrons. Right. So which description applies to an element that has 2 valence electrons? It's a reactive metal. It's in group 2. It's all the way to the left, so it's a metal. And we say that it's reactive because there's less electrons to move around. How does sodium and chlorine both achieve stable electron configurations when they react? An electron is transferred from the sodium, which is a group 1 valence electron, to a chlorine atom, 7 valence electrons, group 7. Well, actually, it's group 17, but it's 7b, depending on what convention you think of. Why do ionic compounds tend to have high melting points? Well, a strong electrical attraction means that the ions require a lot of energy to move apart. So you got to add a lot of thermal energy to break those ionic bonds. The ratio of aluminum ions to chloride ions in aluminum chloride is AlC13. I think that's supposed to be an L. I think this is supposed to be Cl3, and it says it's 3. It's false. It's 1, 2, 3. So I think this is supposed to be AlCl and then subset 3 on the bottom here. I don't know what happened. So the ratio is 1 aluminum to 3 chlorine atoms. So remember that chloride has 7 valence electrons, so it's going to need to borrow 1 electron, And then aluminum is a group 3, or actually it's group 13, which means it has 3 valence electrons. So aluminum can give off its 3 valence electrons, 1, 2, 3, 1 valence electron to each chloride ion. And that's it. Any questions?